So hello everyone, I am Himanshu Mishra, and in this tutorial we are going to solve problem based on the relative velocity concept, and we will also look few problem which is based on the rotational frame of references. So we will be continue solving the problem based on the previous week. So in the previous week we have started solving problem which were based on the rotational motion. We saw that how to find the angular quantities given that we have already mentioned either angular acceleration or angular position, and we might have need to find the angular velocity. So what are the relation? We looked some of these relation, and then when we found that if we have given 2 points, for example, let's say we have a 2 points here, one is rotating and another one is translating, and let's say we have given a rotational motion and we have been asked to find the translation motion. And we look also one problem where we find the where we have given the translation motion details about translation motion like translation velocity, and we have been asked to find the rotational motion of some other bar. So this kind of a question we solve by the relation va equals vb plus relative velocity between them, where let's say a is this point and b is this point. So for example, let's say you have given the angular velocity of this rod, you can easily find the translation velocity vb, and once you get the translation velocity, you can find the velocity translation velocity of a. You just need to keep in mind that both point b and a executing the motion, and these motion are different to each other. They are not necessary to be a same kind of a motion. It can be a different motion. For example, this part is actually rotating while this part is actually translating. So using this relation we can actually find the required velocity. So we will solve few more problem based on that, and then we will look the concept of instantaneous center, where basically using geometrical properties we can arrive, or we can use this equation. So we will be using the geometric property as well as this equation to find the required answer, and then we will move to a next topic where we will try to analyze the velocity of a point using relation similar to this only, but we will be analyzing the motion in the rotating frame. So as of now, all this study happening at the fixed frame of reference, where we fix the frame, Cartesian frame, let's say x and y, and then we analyzing all this motion in the fixed frame. But in those problems we have two frame of reference, fixed frame and the rotating frame. So rotating frame actually rotating with an angular velocity omega, then there is a fixed frame. So in those problem what happens that we need to analyze the velocity or some other quantity with respect to the fixed frame, and those quantity also depend on the additional relative velocity. So here there the velocity at point A will also depend on the relative velocity, and these quantities vb and va are given in the fixed frame. So we will see how to solve such question. Moving on, we can actually start or proceed to the next question. So in this question, the pinion gear rolls on the gear racks if b is moving to the right at 8 feet per second and c is moving to the left at 4 feet per second. Determine the angular velocity of the pinion gear and the velocity of its center A. So this question is actually similar to the previous one. So in the previous question we actually given the angular velocity, but we have been asked to calculate the translation velocity. Here opposite is there, opposite is given. We have given the translation velocity, but we need to find the angular velocity of the pinion. So there are two parts in the question. First we need to find the angular velocity of the pinion, and then we need to find the velocity of a center A. So we will be using the similar relation. So let's fix 2 points C and B. Because we know the velocity of C and B, so C is moving to the left with VC and B is moving to the right with VB, and we know VB, which is 8 feet per second, and VC is 4 feet per second. So it's moving left. VC is moving left and VB is moving right. So we have 2 points B and C. So my velocity at C will be given as VB plus velocity of C with relative to B. Then velocity of C relative to B, as we have discussed in the previous class, will be given by omega cross the position vector between C and B. And between C and B, my position vector is actually the diameter of this pinion. So if my radius is 0.3 feet, then my diameter will be 0.6. So when we, as we saw in the previous class, previous lecture, that whenever we use this equation, we need to identify all the vectors. So we need to identify vector VB, vector VC, and omega vector and our position vector. We need to identify vector VC and VB. So as of now, we have just written down the scalar quantity, that VB is 8 feet per second and VC is 4 feet per second. But when we write the vector quantity, we need to acknowledge its sign as well. So my VC, since it is in the left hand side direction, it will be minus 4I. I, because it's the entire motion is in, the entire component of velocity is in x direction. So this is my velocity vector at point C, and my velocity vector at point B will be positive 8I. This is my velocity vector at point B. Similarly, my position vector will be given as 0.6 J, and my angular velocity, which is unknown, will be given by omega k. So it's the direction of omega is out of the screen, it's in the z direction. So then when we use the equation 1, we have minus 4I equals 8I plus omega k cross 0.6 J. Right? So we have now written down the vector equation. So it has component from x and component from y also. So actually it has only x component. So you can see this cross product. So it's between k and j. And we know that if we take the cross product between k cap and j cap, it will be in minus I cap direction. And the magnitude, for magnitude it is very easy to understand, just multiply omega with 0.6. So this will be my magnitude, and this will be my vector. So this vector will transform to this minus 0.6 omega I cap, right? Similarly, if you take the cross product between j and I, you will get minus k cap, and so on. So this above equation will be minus 4I equals 8I minus 0.6 omega I. So now every term here is in the x direction. So if you write the equation in y direction, it will be like 0 equals 0, and in the x direction it will be minus 4 equals 8 minus 0.6 omega. So it will be minus 4 minus 8 or minus 0.6 omega. So this will give me minus 12 divided by 0.6. So this will be my omega. So when you solve, is 20 rad per second. So the angular velocity of the pinion is 20 watt per second. Now we need to find the velocity of center A, and it is pretty much easy, right? Because we considered 2 points C and B, and we use this relation on those 2 points VC VB plus the velocity of C with respect to B. Now if we want to find the velocity VA, we have to repeat the exercise. So now we consider point A and point B and use the same equation, but instead of C now we have point A. So it will be VA equals VB plus velocity of A relative to B. Velocity of A relative to B will be omega cross product with omega, which is rotational motion of the particle, having the cross product with position vector AB. So this is my position vector, this, which is the radius between A and B. So now I need to identify all the vectors. So my VA is unknown, which I have to find. My VB, which we already defined here, plus 8i. My position vector is 0.3j. So earlier it was a diameter, so it was 0.6j, which is position vector between C and B. Now the position vector between A and B is just a radius in the y direction, so it's 0.3j. And my omega, we already know, it's 20 in the jth direction, which we found out. So VA vector is 0.8i plus 20 in the z direction, cross product with 0.3j. And we can evaluate this term first. The cross product between k cap and j cap will give answer in minus I direction, and the magnitude will be 20 multiply 0.3, which is 6. So the above equation is VA 0.8i minus 6i. So VA will be minus 5.2. In the x direction, and this is minus sign, which means it is going toward left hand side direction. So this is my actually the direction of VA. Sorry, this VB was 8, right? It is not 0.8, it is actually 8. So this will be minus 2, plus 2i meter per second. So this will be my velocity at point A. So sorry for this confusion. So this, my velocity A will be in the right hand side direction because it's positive 2 meter per second. So this is my velocity at point A. So just to recap, we have given a pinion, which is, and also the rack. So we have given 2 points in the rack B and C. So we have given the translation velocity of point B and point C. So we know that if we have given 2 points and if we need to find the velocity of 2 points, we have to use this equation where the velocity of one point can be given by velocity of other point plus velocity of that point with respect to the other point. So when we use this equation, first we need to identify all the vectors. So we identify all the vectors and we actually calculate the angular velocity, which we need to find. But then in the other part of the equation, we need to find the velocity of other point A. So then we consider that point, which is A, and we consider previous point B. So again it was the same question but with a different point. So we now consider 2 points A and B. Repeat the exercise, identify all the vector and solve, and we got the velocity of point A, which is 2 meter per second in the x direction, the positive x direction, which means the velocity of A it's toward right hand side. So let's move to the next problem. So in this we have, if the gear rotates with an angular velocity of omega 10 rad per second and the gear rack moves at velocity at c, which is 5 meter per second, determine the velocity of a slider block A at an instant shown. So this is a similar problem. We can identify, because we already know the equation, what equation we need to know. And now we also know the points. So we have given Vc, velocity at point C, which is 5 meter per second. We have given the angular velocity, which is 10 rad per second. So this is, Vc can be our one of the point. So point C can be one of our point. Then we can have this point as B, and then we can have this point as A. So first, using the same expression, we can actually find the velocity at point B, and then again use the same expression between point B and A to find the velocity at point A. So we use the same formula first between 2 points C and B, then between point B and A. Like before in the previous question, we use this formula between point C and point B to find the omega. Then we use the same equation between point A and point B to find the velocity at point A. So it is a similar one we can use between C and B, and then B and A. So between C and B we have Vb equals Vc plus velocity of B relative to C, and this can be given by omega cross r with respect to C, which is this radius. So identifying all the vectors, so omega we know, which is 10 rad per second, and we know the position vector also, which is 0.075 in the y direction. Vc we know, which is in the left hand side direction. So if you draw the axis Cartesian coordinate, you will know it is actually in the minus x direction. So it is minus 5i meter per second, and we need to find Vb. We don't know anything about Vb. So it will be minus 5i plus minus 10k cap cross product with 0.075 j. So my Vb will be minus 5i. So first evaluating the cross product term. So we already know, we have solved many problems. We know that if we take the cross product between k and j, we will get answer in minus I direction. And for magnitude, we just multiply this and this scalar quantity. Which will give us 0.75, and this minus and this minus will be getting positive, so it will be positive 0.75 I. So both are in the x direction, both are I cap and I cap, so we can just do the addition and subtraction exercise. So we will get Vb as minus 4.25 I meter per second. So this is my Vb. So this is my translation velocity of point B. It's a minus sign, minus 4.25, which means the direction is toward minus x-axis. So this is minus 4.25 meter per second. This is my VB. So now I have point B. Now I can consider another point A and use this same relation between point A and B. So earlier we used this relation between point C and B. Now we can use this relation between point A and B. We know the position vector between A and B, which is 0.5, and this is at 60 degrees. So we can take a component. So this component will be x and this component will be y. And this, if this is my point 1.5 meter, we will know that the x component will be 0.5 cos 60 and y component will be 0.5 sin 60. So now using the same relation between point A and C, between point A and B, sorry. So this will be VA equals VB plus velocity of point A relative to B. Velocity of point A relative to B will be omega cross R AB. So this omega is actually the angular velocity of this rod, 1.5 meter rod, because as B is translating in the left hand side direction, this rod is trying to go down, this end is trying to go down, and this part is trying to go in this direction, left hand direction, and this part, sorry, this A part will trying to go up. So it is rotating like this. And let me call this as AB. So identifying all the vectors, so my R position vector will be minus 0.5 cos 60 plus 0.5 sin 60 j cap, right? And this is because this is actually based on the trigonometry, nothing very special about the position vector, how we got it. Basically you draw one line here, one line here, so this is 60 and this is 1.5 meter. So this will be 0.5 sin 60 in the y direction, and this will be minus 0.5 cos 60, this part. And this in the x-axis and this in the y-axis will be our position vector. We can simplify this further and solve this. So this will be minus 0.25 I sorry, this was 0.5 meter, not 1.5. So this will be 0.433 j. So this is my position vector. So I don't know anything about omega vector. We have not found anything about omega AB, and VB we know, VB is 4.25 in the x direction. So when we use this equation, let's say this is equation number 2, we don't know omega AB, but we know the direction of it, because since it can be rotate in the anti-clockwise or clockwise direction, but the direction is always perpendicular to the screen, that is in the jth direction, and the cross product with 0.25 I cap plus 0.433 j cap. Now we can always first evaluate this term, which is a cross product term, and we know that if we take the cross product between k and I cap, we will get the answer in the j cap. If we take the cross product between k cap and j cap, we will get the answer in minus I cap. And the magnitude will be omega AB multiplied by 0.433. And here the magnitude will be omega AB multiplied by 0.25. This will be minus also because it's in the clockwise direction. So when you simplify this based on above argument, you will have 4.25I. First consider blue color direction and magnitude. So it will be 0.25 omega AB in the j direction. And this will be minus 0.433 omega AB in the I direction. So my VA, so now we have a vector equation in which components are there in both the direction. We have the components from x-axis and we have components from the y-axis. And we know one thing, so you can see in the figure that this VA can only be in the y direction. So VA could be either this or this. VA cannot move in the x direction because it has this restriction where velocity of point A, VA can only allow in the y direction. So this vector VA is actually in the y direction only. So if we split x component and y component, we will have x component which is 4.25 this is my x component equation. For this is my x component, this is my x component. So when you solve this, you will have omega AB which is 9.81 watt per second. Now if we write the y component equation, so this is in y component and this is in y component, both have j cap. So it is VA equals 0.25 multiplied by omega AB. So this will be 0.25 multiplied by 9.81, which is my omega AB. So my velocity of point A will be 5.66 meter per second. So this will be my velocity of point A. So just to recap here we have given a problem where a gear rotates with an angular velocity 10 rad per second and gear rack move at 5 meter per second, and we need to calculate the velocity of a slider. So what we did, we considered first point C and point B first to calculate the velocity of VB by using this relation. So this relation we use between point C and point B to calculate the velocity VB. Then we repeat the exercise where we consider point A and point B and we use this relation between these 2 points. So first when we use this relation between point B and C, we actually get the velocity of VB which is minus 4.25 meter per second. Then when we use the same relation between point A and B, we actually get this vector equation, and it has a component from, it has x component and y component. It has both x and y component. So we divide this equation into a scalar form, where first we consider only x component. From this was my equation 1, and we got the angular velocity omega ab. Then we split the y component, and from this y component we actually got the velocity of point A, which is 5.66 meter per second. So that's it for the this topic. Now we will move to our next topic here. I mean, it is almost the same topic. We will be using the same relation, but we will be solving the problem which will be based on instantaneous centers. So what is instantaneous center? For example, let's say you have an arbitrary body here, and there are 2 points. So this is point A and this is point B, and this point A is moving with velocity A, and this point is moving with velocity V. So you can actually visualize this motion as a pure rotation motion. So even though the velocity of point A and B have some translation velocity, which means this velocity is moving, having some translation motion, but despite of this, you can actually visualize this motion as a pure rotational motion. And in order to visualize the rotation motion, you need to fix a point about which this rotational motion is occurring, because you can see this VA and VB, they are the translation velocity, which means this point is moving, it is changing the position. So this is my point A, after some time it will reach here, then after some time it will reach here, and so on. It is moving. And similarly for point B, both executing the translation motion. But now I'm saying that you can also visualize this as a pure rotational motion, in which you consider some fixed point. Let's say this is my fixed point O, and above this fixed point, what happens? This both point above this is my fixed point O, and this both point trying to executing the rotational motion about this fixed point. This is my point A and this is my point B. So both point actually exhibiting a rotational motion. So this fixed point is actually the instantaneous point. So in order to visualize this, we need to have a displacement vector which should be normal to the velocity, and this can be originating from point A to point O and point B to point O. So this is my R A with respect to O, and this is my RB with respect to O. So in this problem now we will be using the same relation, but first we need to identify this position vector, which is the vector between point B and the instantaneous center. So this, whenever this line meeting with each other, so this line and this line actually meet here, let's say it's meeting at point O. So whenever this, at the location where these two lines meet each other, this location is actually the instantaneous center, because at this location my translation velocity is 0, and this is the fixed location from which my point A and B is exhibiting the rotational motion. So when we actually assume or visualize the motion of point A and B as the pure rotational motion about point O, we can use the method of instantaneous center, because then we can actually identify the position vector, and then we can use the similar relation that we have been used from previous class to find the velocity at point A or other at velocity at point B. So in the previous question we assumed that VA and VB are the translation velocity. This is not actually assumption, this is actually a fact. VA and VB are the translation velocity and the point A and B executing translation motion. But in order To solve the same problem using the instantaneous center, now we change our visualization. We now say that these 2 points are rotating, not only moving. These are rotating, but they are rotating about some fixed point, and in order to get this fixed point you need to draw normal, which is the position vector, and this is the normal to the velocity. So you need to draw the normal for both point, and when the location where they are intersecting, these normals are intersecting, this will give you the instantaneous center, where the velocity, translation velocity, will be 0, and this is the point where these A and B exhibiting the rotational motion. So in this concept, our idea is to calculate this position vector and use this information here in this equation, because we know that we solve many problems from this equation, and we know that this velocity of point A with respect to B actually depends on this position vector. So we will know this position vector from here, from instantaneous center concept, and then we can use this relation to find the velocity at point A. So let's solve the first problem based on this. So here at an instant shown, so one more thing, so we have seen that we have 2 points here, VA and VB, and we draw the normal in order to find this position vector, and we found the location where these normal are intersecting with each other, and that point we call the instantaneous center, this point. An instantaneous center can be outside of this body, it can be also inside the body. So for example, if you consider an example, let's say this is our body, this is our point A, and this is our point B moving with velocity V, A with velocity A. Now both are moving in the opposite direction with some magnitude, which is VA and VB. So what should be the instantaneous center in this case? Because as we discussed, the instantaneous center should always be normal to the velocity vector. So for point A, this should be this, and for point B, this should be this one. So this will be my instantaneous center here, this point. So unlike in the previous case, my instantaneous center, this one, actually lies outside of this body, but here the instantaneous center lies inside the body. So it can lies either outside or inside the body. It actually depends on the direction of velocity. Now having discussed this, let's solve first question. So at the instant shown, the disk is rotating at omega 4 rad per second. Determine the velocities at point A, B and C. So we need to determine the velocity at point A, B and C. So you can see that as this disk is rotating, this is my direction of VB, this is the direction of VA, and this is the direction of point C, VC. So you have our disk, let's say this is your C, this is our B, and this is our A. This is my VC, this is the velocity of point B, and you can, if you try to find the position vector with respect to A for both C and B, it should be normal to the velocity vector, this, and this should be the normal to, and between A and B, when you try to plot or draw the position vector between A and B, that vector should be normal to VB, this one, and it is actually meeting here. You can see it is actually both this vector and this vector is actually meeting here. So this is my instantaneous center, about which my point C and point B exhibiting pure rotational motion. So this is RCA and this is RB with respect to A. And we need to identify this vector. Right, so this is my radius, this is my radius R, this is my radius R. So this can be actually determined by Pythagoras theorem, because I already know this R and this R. I already know this side and this side, so I can determine this also. So the magnitude of this can be given by 0.15 square plus 0.15 square. So it will be, the magnitude will be 0.212 meter, and this position vector is very easy to identify because this is the diameter of this disk. So the magnitude of B with respect to A will be just 0.15 multiplied by 2, which is 0.3 meter, right? So now you identify this length and this length. My VC will be omega multiply R. I am writing in the scalar form, and R is RC with respect to A. And my VB will be omega RB with respect to A. So my velocity at point C will be, omega is given, which is 4 rad per second, and RC with respect to A is 0.212. So VC will be 0.848 meter per second. Similarly, I can find VB, which is omega, which is 4, and RBA, which is 0.3. So my VB will be 1.2 meter per second. So as you can see that we have used the same concept that we have been used in the last two class. Same formula and some very basic mathematical relation. But only difference here is when you use the instantaneous center, it is very important to calculate the position vector, which is the displacement vector between point C and the instantaneous vector. So here A point is the instantaneous center. So you have to determine the position vector between some point X, between X and instantaneous center. So this is the position vector which is very crucial to identify. So previously whenever we solving problem, we were not very emphasized on this position vector, because we saw that in many problems we can easily solve for this position vector. We were not very much worried about the position vector, but when we use the instantaneous center method, it is very crucial to determine this position vector. So we determine the position vector by using Pythagoras theorem, and for the position vector between B and instantaneous center, it is very easy because it was just a diameter. So once we get that, then we use our general equations to calculate the velocity. So let's solve a problem where we just need to identify the instantaneous center graphically, not any numerical problem. So in each case, show graphically how to locate the instantaneous center of zero velocity of link AB. Assume the geometry is known. So let's first consider case A. So we need to identify the instantaneous velocity of link AB. So basically we need to identify the direction of velocity of point A and B. So you can see this actually rotating in the counterclockwise direction. So you can visualize as this is rotating in the counterclockwise direction, this point should move in this direction, right? And as this point is moving in this direction towards a little right direction, this point should move in the upward direction, upward right direction, because this point, this actually trying to move like this, like this. So this point is moving lower right and this point is moving upper right. So if this is my AB, so this is one of the direction of VA vector, and this is one of the direction of VB vector. And now we need to find the instantaneous center. So for that we need to make a normal vector from point A and point B. So when we make the position vector, which should be the normal to VA, so my position vector from A should be normal to VA. So it should be normal, so it should be like this. And my position vector of VB from B should be normal to VB, like this. So where the location where they intersect here, this is my instantaneous center. So this is RAIC and this is RBIC. So with this instantaneous center, both point A and B exhibiting the rotational motion. You can actually visualize this is my fixed point, which is my instantaneous center, and about which this A and B is actually exhibiting rotational motion. So whenever we're solving the problem, we have to use the same concept that we have been using in an earlier class, but for that first we need to find these instantaneous position vector from point A to the instantaneous center and point B to the instantaneous center. So this is the crucial. Finding this vector are crucial. So once we find this vector, then we can use our old formulas to calculate the unknown. Similarly, we can draw figure B. So this is rotating with an angular velocity omega. So as this is rotating with an angular velocity omega, this is actually going in this direction. Point A is actually moving in this direction. Right? You can visualize this. This is going down, so this point is going like this. And as this point A is going like this in the lower left, the point B should go this, because here it is constant. Point B cannot go in the y direction, completely in the y direction. So it's actually depend on the direction of point A, but as this is my direction of point A, my direction of point B will be in this direction. So you can draw the normal. You can draw the position vector from B, which is normal to VB. This is my VB, this is my VA. So if you draw the position vector from point B, which is normal to VB, this is my position vector, and for point A, this will be my normal position vector, because it is normal to position velocity vector VA. So this here it is intersecting here, so this is my instantaneous center. So this will be position vector A with respect to instantaneous center, and this will be position vector B with respect to instantaneous center. Similarly, we can Now draw C. So you can visualize in this figure itself, so as it is rotating in the counterclockwise direction, this point A actually moving in this direction, right? And as this is trying to go down, this will go in this way. Sorry, as this try to go down, this will go in this direction. So my position vector from point A should be the normal to this velocity, should be this. So this should be this, and this should be this. The position vector from B should be normal to VB, and it is actually intersecting here. So this is my instantaneous center. So this is RA with respect to instantaneous center, and this will be RB with respect to instantaneous center. So in this figure we actually identify few cases where we draw the instantaneous center based on the direction of velocities at points. So first we need to identify the direction of velocity. So this should be based on pure visualization. Once we identify the direction of velocity here, then we just draw the normal and see where it is intersecting, and that intersection point will be instantaneous center. So let's solve a problem. So if link CD has an angular velocity of omega CD, which is 6 rad per second, determine the velocity of point B on link BC and the angular velocity of link AB at an instant shown. So it was looking like a previous problems that we have discussed, that if we have given 2 points, then we can actually use this relation. The only thing is we solve this problem by using the instantaneous center. So first we will actually identify various position vector, and once we identify this position vector, we can use this equation. So you can see first we need to identify or find the velocity, translating velocity at point B, and then we need to find the angular velocity of a link AB, and we have given the angular velocity of CD. So if we have given the angular velocity CD, which is 6 rad per second, we can actually find VC by using this relation R omega. Because R is 0.6 and omega is 6, we can find VC. Once we get translation velocity of point C, let's say, which is in this direction, we can consider 2 points C and point B, and we can use this relation between these 2 points, because we know that if we have given the motion of 2 points and the motion of these 2 points are different with each other, we can use this relation to find the velocity of one point, given that we know the velocity of other point. We have been solving such problems since previous class, so based on that, since we already know C, we can actually find VB. Right, so my VC will be omega CD multiplied by R CD, which is 6 into 0.6. So this will be 3.6 meter per second. And I can write VB as in a similar manner, which is omega AB multiplied by RAB. And this RAB I can found. So this is my 0.6 meter and this is at 30 degree. We can actually find this, which is my RAB. So basically I am now here concerned about the magnitude of RAB. So this is 0.6, this is RAB, this is 30. So RAB will be 0.6 sine 30. So RAB is 1.2 meter. So my VB will be 1.2 omega AB. So we don't know the magnitude of omega AB. So now we can actually identify the instantaneous center because we know that it is rotating counterclockwise direction, which means the velocity of point C is toward left. If this is rotating in the counterclockwise direction, then this will be the direction of my VC. And if this is my velocity vector at point C, then what is the position vector? It should be always normal. So this is the normal. Right? And now if C is moving left hand side direction, my VB should move in this direction, right? Because this will rotate like this in the counterclockwise direction, and it is rotating in the counterclockwise direction. This point B will rise. Right? So this is my point B, this is my point C. It has the velocity vector in the left hand side direction, and it has the velocity vector like this. So this is my this is my position vector, which should be position vector of B, which should be normal to the velocity vector VB. And for C, this should be my position vector. Now where it is intersecting? It is intersecting here, which is my instantaneous center. So this is my RB with respect to instantaneous center, and this is RC with respect to instantaneous center. And since if this is 30, then this should be 30, this should be 90 because it's normal, and this should be 60. And we know this distance between B and C is 0.3 plus 0.3. So the distance between B and C is 0.6 meter. So I can find this distance and this distance by using trigonometric relations. So 0.6 RB with respect to IC is cos 30. So RB with respect to IC is 0.6 by cos 30. So this is 0.692 meter. And RC with respect to IC divided by RB with respect to IC equals sine 30. So RC with respect to IC will be RB with respect to IC sine 30, which is half. So RC with respect to IC is 0.346 meter. So this is my position vector from C to IC, and this is my position vector from B to IC. Now I can write this VC equals omega CB multiplied by RC IC, because this is my B and C and this is my direction of C. So basically I'm actually finding the rotational motion between C and B by this relation. So this will give me omega CB equals VC divided by RC IC. So VC is, we know VC, we found VC as 3.6 meter per second, and RCIC is 0.346. And this is 10.4 rad per second. And then how we calculate VB? We can use a similar formula. VB equals omega CB multiplied by RB with respect to IC. Because when we use the instantaneous center, since this BC part is moving with angular velocity omega, this is omega BC, the position vector should be this instantaneous center. For B it is RBIC, for C it is RCIC, because it is rotating with this position vector. So when we calculate the velocity V, we have to consider its position vector with respect to IC, because it is rotating with that. So this is why this position vector, combination of position vector, when we are using, so my point is we are actually using this formula and this is not new to us, but what position vector we need to consider, that is new. Because when we use the instantaneous center concept, we can see it is very simplified, because now we actually identify this instantaneous center, which is this and this. It is my point B is rotating with this normal vector and my point C is rotating with this normal vector. So when I use this formula, my normal vector should be between that point X, which is B, C or A, with respect to IC. When we don't use this concept, instantaneous center, we cannot just use any position vector. There we need to use the position vector about which the body is rotating. Like here, about point A it is rotating and about point D it is rotating. So we cannot use this equation very blindly, because when we don't use instantaneous center, here about point A, the point B is rotating, so we have to use VB omega AB and the distance between A and B. So even if you know the distance between A and B, you don't know omega AB. But when you use the instantaneous center between B and C, you found that you can actually use omega BC, which you already found, because you know VC, because you use the same but now you can use the same equation, VC omega CB RCIC. So you know this, so you can actually found omega CB. Then you use the same relation for another point VB, and it is rotating with this with this position vector. So you now already know omega, you have to find VB, but you know omega CB, you know position vector, and then you can easily find VB. When you don't use position vector, as I shown here, then you have to use distance between point A and B, because about point A only it is rotating. But then you have to consider omega AB, this omega, which you don't know. So the instantaneous center concept allows you to use this equation in a manner where you already know two quantities, either V or omega or R, to find the third unknown. But when you don't use instantaneous center, you need to see which point is fixed about the motion, rotational motion is occurring. Here it is point A and point D. Then you can only use either CD or AB. When you use CD, you need to consider the omega of CD bar. When you consider AB, then you need to consider omega between AB bar. So you need to know these angular velocities in the beginning itself, and this sometimes make very question very difficult, because you rarely knows all the angular velocity at the beginning. So this instantaneous center actually allows you to calculate the omega by some imaginary position vector about which the rotational motion is occurring, because the rotational motion occurring above this instantaneous center, and you are finding this some imaginary instantaneous center, which allows you to use this formula more conveniently. So this is the advantage of using the instantaneous center. So when we use at point C, we actually found out the omega CB. Now we know the omega CB, we know this, we can actually find VB. So my VB will be omega CB is 10.4, and RB with respect to IC we found is 0.692. So this will be 7.17 meter per second. So now you know the velocity of point B. Now you can use this formula to find omega AB, because as we discussed, we don't know omega AB and we didn't knew VB, but now we knew VB, we can actually find omega AB. And this relation is not based on the instantaneous center. Remember that this relation is not based on instantaneous center. It is a very general relation that we discussed in the previous class. We are using the instantaneous center concept inside this relation. So this is a very general relation. So when we don't use instantaneous center, you will have this relation VB, which is omega AB RAB. Now you calculate VB, so now you can calculate omega AB. But before that we didn't knew VB, we didn't knew omega AB, so it was very difficult to use this relation. So now when we use this relation, omega VB equals omega VB and the distance between A and B, because it's a simple logic. This is my B, this is my A, this is rotating, so it has some translation velocity VB, this, and it is rotating, then this should be my RBA, the length of that rod. So my omega AB will be VB by RAB. So this is just a length, it is not some instantaneous, the distance between instantaneous center and some point B. It is just a length, so it will be VB 7.17 divided by RAB, and RAB is 1.2 meter. So this will give me 5.98 rad per second. So this will be my omega AB. So just to recap, because it was a very interesting question, because we cover a lot of concept in this concept, so it is better to visualize or recap this. So here we have given that my CD link, this CD was rotating with some omega CD. and as it is rotating, this point is moving, translating like this, and this point is translating like this. So we need to find the angular velocity of omega AB. So we need to find omega AB. So let's consider the case where we don't use instantaneous center. So what are the things we can use then? So first we can use VB equal VC plus VC with respect to B. So we are using this formula from last class. So we can use this formula. But to use this formula, you need to first calculate VC with respect to B, which is omega CB cross product with RC with respect to B. So at this position you can find RCB because it is 0.6 meter. But you don't know omega CB. This you don't know, and also you don't know VB. So you can actually write this equation in a vector form like this: VB equal VC plus omega CB. These are the vector cross product with RCB vector. And you can decompose this vector quantity into x component equation and y component equation. So this is unknown and this is unknown. So from x component and y component equation, you can actually find these two quantities because two are unknown. So you need two equation, which is x and y component, and you can actually calculate this. So when you calculate VB and omega CB, then you know VB. Then what you can use, you can actually use this relation, which is VB equal omega AB multiplied by RAB. Basically the concept we are using is, if this is my point B, it is, and this is the direction of velocity VB, this is point A, then it should rotate like this with some angular velocity omega AB, and it has a distance RAB multiplied by this distance. Then you can use this relation because you know omega VB, you know omega CB. You don't need to use omega CB, you can just use VB and this relation to calculate omega AB. So this is without instantaneous center. But when you use the concept of instantaneous center, you just find the VC as usually, and this is the expression of VB as usually. Then based on this direction here and here, you identify the position vector which should be normal to the velocity vector. So this is my position vector from point B normal to VB, and this is my position vector from point C which is normal to VC, and this should be my IC. So this is my RB IC and this should be RC IC. Now you use this equation V equals omega R, this equation, but now R is my instantaneous position vector. It is not this length, it is not this length, but it is instantaneous position vector. So my VB will be omega BC RBC IC, and VC will be same omega BC because they have same angular velocity. Both we have considered these 2 points, and these 2 points should share same angular velocity. So from this relation you actually find that angular velocity V omega BC, and then from this relation you actually find your VB. Then once you find VB, the step is common. You use this equation to find omega AB. So we just discussed this problem based on instantaneous center method and also method which is not belong to the instantaneous center method. There you need to use this relation when you don't use instantaneous center method. And when you use, you can able to solve by using this relation alone. So when you use this relation, it is not that you are not using instantaneous instantaneous center method, so you have to use this relation. It is nothing like that. You are just not concerned about this position vector. So when you don't use instantaneous center method, you don't concern about this position vector. So even if you use this formula, you don't concern about this position vector. That's all. I'm trying to say. It is not like if you are not using instantaneous center method, then you always have to use this formula. It's not like that. You can use instantaneous center method and also this formula. The only thing is you need to find this position vector, which is a vector between point, some random point B or C, and instantaneous center. So even if you use this formula, when you use instantaneous center method, you are concerned with this position vector between instantaneous center and point B or point C. So you can either use this formula or this formula. When you use the instantaneous center method, you just need to calculate this position vector between instantaneous centers. That's all. But when you don't use instantaneous center method, you don't need to concern about this position vector. There you actually use this position vector, which is the length of this rod, and use this formula, or you can use this formula also. Here also, when you consider position vector, it will be not this, it will be just the length of the rod. So either use length of rod or use position vector between point and instantaneous center. So this is the method that right now we are discussing, instantaneous center method, and this is the method that we have discussed at the beginning of this class and also in the previous class, where the position vector based on the length of the rod. Here the position vector based on the position vector between point and instantaneous center. And in this problem, we discussed this problem by both the methods. Even though I have written down all these steps for the instantaneous center method, after solving this problem, when I revised, I briefly discussed without instantaneous method also, where we have to use this relation and this length as a position vector, this length as another position vector. So let's solve another problem. So at the instant shown, the truck travels to the right at 3 meters per second, while the pipe rolls counterclockwise at omega 6 rad per second without slipping at B. Determine the velocity of the pipe centers G. So you can see as this pipe is slipping by some omega, angular velocity omega, this point G is moving in this direction and this point B moving in this direction. So you have this pipe, this is G, this point is moving in this direction and this is B, this point is moving in this direction. So what should be the instantaneous center? As we discussed previously, this is the normal vector of point G and this is the normal vector of point B. So and this should meet somewhere here. So this is my instantaneous center. So my VB will be omega, this is RB with respect to IC, and this is RG with respect to IC. RB with respect to IC, and my point G will be omega RG with respect to IC. So now we are using instantaneous center method. I will also discuss how to use without instantaneous center method, and that method we already discussed in the beginning of this class and the previous class. So we can use these two formulas. So we know the truck travels to the right at 3 meters per second. So we know velocity of B, which is 3 meters per second. And we know the omega also, which is 6 RIC. So my RBIC will be 3 by 6, which is 0.5 meter. This is my position, magnitude of position vector B with respect to IC, this quantity. Now we need to find this quantity, and we know the radius, which is 1.5 meter. So my RG with respect to IC plus RB with respect to IC is equal to the radius, which is 1.5 So my Rg with respect to IC will be 1.5 minus Rb with respect to IC. So this is 1.5 minus 0.5, so this will be 1 meter. So now we found RGIC, we know omega, which is 6. So my Vg will be 6 into 1, which means 6 meter per second. So this is 6 meter per second, and this we already know 3 meter per second. Now if you don't want to use instantaneous center method, you can use Vg equal Vc plus Vg with respect to C. Then Vg will be Vc plus omega Gc cross product with length between Gc. Now you are not using instantaneous center method, so here the position vector is not this, it is actually a length between G and C when you don't use IC. So what is this? It is just a radius, which is 1.5 J, and this we know it is given in the equation 6 rad per second in the counterclockwise direction, so it's 6k. And this we know Vc, which is right hand side direction, 3 meter per second, which is 3I. This will give me k into J. So this will give me the direction minus I, and the magnitude is 6 into 1.5, which is 9. So this is minus 9I. So my Vg will be 3I minus 9I. So my Vg will be minus 6I meter per second. So this is my velocity vector, minus 6I. Minus means my direction of Vg is left hand side. So this is my x direction, this is my minus x, this is y, this is my minus y. So this is the direction of Vg, minus 6I. So this is the method without instantaneous center, where we use this equation. We identify the vectors. Vc is this, omega is this, position vector is this, and the position vector is the length between point G and C. So when we solve using this, we get the Vg vector, which is minus 6 in the x direction. But when we use the instantaneous method, we only use this relation and this relation. The major part is we need to identify the position vector, which is not a length between B and G, but it is the length between B and instantaneous center. This is the length between G and instantaneous center. So first we figure out these two quantities. Rb with respect to IC is 0.5 and Rg with respect to IC is 1. Once we figure out this quantity, we just use this relation to find the answer. Because if you want to know the rotation along a fixed point, so this is fixed point O, and if you want to know the rotation of A having the velocity A, we just need to use formula, which is omega A multiplied by RAO. So here RAO is the instantaneous center that we need to figure out. So whenever you use instantaneous center method, most probably you will be using this scalar relation. The only thing is you need to identify R first. That's the only thing. So we solve this problem based on with instantaneous center method, and also without instantaneous center method, where we use this relation. So let's solve one more. So now let's move to the different concept. So until now we are actually trying to solve the problem in the fixed frame, which means that you identify the frame. Let's say this is my x, this is my y. The motion is occurring between this plane. So this point is actually moving to this position and then to this position. Whatever the analysis we are doing, we are doing at this fixed frame. We just fix the frame and we see that how this point is moving arbitrarily, and we just finding the velocity of this point by using various technique like with instantaneous center and without instantaneous center. Now we will see the motion in the rotating frame. For example, let's say you have point B and you have point A. So this is the position vector RB from O, and this is the position vector RA. Now let's say my point A is moving, and let's say there is a coordinate axis at point B. So this is Y, this is X. And this coordinate axis is actually rotating with angular velocity omega. Here omega is theta dot, because this theta is changing with time, and the rate of change of theta is actually omega. So what you are doing now, you want to analyze this point motion in the rotating frame of coordinate. So for this, first, as usual, earlier when we deriving this equation, so this equation when we use in the previous class and at the beginning, so we use this equation to solve many problems. So this equation is valid only for the fixed frame. But now we are concerned about this rotating frame. We need to analyze the motion of point A with respect to point B, and point B is actually lies in the rotating frame coordinate x, small x and small y, and it is rotating. So the example of such motion is, let's say you have a fan. So you have this fan which is moving. Let's say this is a pump. This is a fan of a pump, and there is a water at this fan, water droplets at this fan. So as this blade is moving, this drop is also exhibiting some kind of a motion. So you have to analyze the motion of these drops in the rotating frame, because this blade is moving and the drop is placed on the blade, and drop have their own motion, drop exhibiting their own motion, and the drop's motion has to be visualized in the rotation frame of reference. Similarly, let's say you have a disk and there is a portion and there is a ball inside the disk, and this disk is rotating and this ball is moving. So as this disk is rotating, this ball is also exhibiting some motion, and to analyze the motion of this ball, you need to consider the rotation frame of reference, because this disk in which you place the ball is rotating. So this disk is actually acts like a frame of reference which is rotating. So for such problem, we need to analyze the motion of A in the rotating frame of reference. So my XY is the rotation frame of reference, and my capital XY is the fixed frame. So until now we actually analyze the problem in the fixed frame, and this by using this relation, and now we actually derive the relation in the rotation frame, where we account the rotational frame of the coordinate as well as the fixed frame. So basically we will write the velocity of point A, which is based on the velocity, and this is based on the fixed frame, and based on some velocity which is based on the rotation frame, like that. So when we derive this expression, we actually write down the position vector RA with respect to RB plus position vector between RB and A, and we do the same thing here. So if my position vector, this is my R, so I can write RA equals RB plus R. And this R is in the rotation frame. You can see here it lies in the rotation frame, which is given by small x and small y. So I can write this as RA equals RB plus xi plus yj. So now we will take a time derivative, but when we take the time derivative, you can see this rotational frame x and y is also changing. The angular velocity or the position uh, of any point, or this uh, component x and y itself is changing because it is rotating. So this quantity I and j cap will also change, and x and y will also change in time. So when you divide this equation or take a time derivative of this equation, you will have r dot a plus equals rb dot plus xi dot xi cap dot plus y j cap dot plus x dot I cap y dot j cap. And in the previous class, we actually, when we were analyzing the curvilinear coordinate, we saw this, that if you have position vector et, tangential unit vector et, and if it changes to tangential vector et dash, then this is my change det, and this change was in the normal direction en. So this is my normal direction, and the magnitude of this change was theta, and that we actually represent theta with d beta. So this will be d beta. So this will be my vector. So my det is in the normal direction. You can see both are in the same direction, and the magnitude of change will be given by theta or d beta, whatever you define here. Similarly, the change in I component will be defined by in the direction of j component and the direction of theta. The change of j direction will be defined by d theta minus d theta and I direction, like that. So when you take the time derivative of this quantity, you will get I cap dot equals theta dot j cap dot minus theta dot I cap. So you can use these relations here. So when you use this relation, you will get VA equals VB plus omega cross R plus V relative velocity. So this is the velocity of point A with respect to B in the rotational frame. So this velocity is actually identified in the rotational frame, whereas this velocity are in the fixed frame. So earlier we used the relation VA equals VB plus omega cross R. This was in the fixed frame. But now when we consider the rotational frame of reference as well, we get additional velocity, which is a relative velocity, and that is actually defined in the rotational frame of reference. When we take the time derivative of this equation as well, we can write down the equation of acceleration of point A as AB plus omega dot cross R plus omega cross R plus 2 omega cross with relative velocity plus relative acceleration. So this is my expression of acceleration. So the problem that we will going to see, which are based on the rotational frame of reference, you just need to consider these two equations in order to find the velocity and acceleration. That's all. You need to identify all these terms, omega r, velocity, relative acceleration, in order to use this formula. So it is just substituting the formula, that's it. You just need to identify various components like omega, position vector, relative velocity and relative acceleration, and that we will identify whenever we solve the problem. So you can see this is a tangential component of acceleration. This is the normal component of acceleration, and this is a Coriolis acceleration. So this you will get only when you have a rotational frame of reference. If you don't have rotational frame of reference, you will never get this Coriolis acceleration. And this is the relative acceleration in the rotational coordinate. This is also in the rotational coordinate. So the rotational coordinate always brings some additional terms in the acceleration, which is the relative acceleration and also the Coriolis acceleration. So we will use this equation in order to solve the problem. And we saw in the previous classes, like whenever we try to use this bigger relation, the most of the problem was actually the substituting based problem only. You just need to substitute these formula, that's it. So it's not a very complicated formula. The only thing is you need to identify these quantities. That's the only thing. Once you identify these quantities, you can just use these equations directly to calculate the velocity at any point. And this is what we have done in the fixed frame of reference when we use this relation. So this is for fixed frame and this is with rotational frame. So until now we actually solved the problem by using this relation which is valid only in the fixed frame, and for that we have used multiple method. We use with instantaneous center, where we determine the position vector, which is the vector between any random point x and instantaneous center, and also we use without instantaneous center method, where we consider the position vector which is based on length of rod. So all this method we used in the fixed frame, but in the next class now we will solve the similar problem, but now it is in the rotational frame, and we will see it is not very hard problem. We just need to use this expression. Only thing is we need to identify all these quantities. So that's it for the today's tutorial. In the next tutorial we will solve the problem which will based on the rotation frame of reference, and then we will start solving problem which will be based on impulse, change in momentum, change in angular or linear momentum, and so on. We will see that how momentum varies as the velocity decrease or increase, and what is the role of impulse, when we can use the concept of impulse. And after that we can actually try in considering or solving problem based on the work energy relation, where we use the work energy or virtual work concept in order to determine the force or the motion of a body. So after the this concept, rotation frame of reference concept, we will be moving to the problem based on the kinetics, where we actually concern about force and motion of the body. So we can relate with two. So if we have given force, we can actually find velocity or acceleration, and if we have given velocity and acceleration, we can actually find force. So until now we are not talking about force. We are just given various component or various quantities of motion like velocity, acceleration and position, and we are just jumbling between them. We are finding position when we were given velocity and acceleration, and we are finding velocity when you were given acceleration and position. We are not concerned about force at all. But after this rotation frame of reference, we will move to kinetics topics, when we see how the velocity, acceleration influence force, or how force influence velocity and acceleration. And there we will be using Newton's second law, where we say that my force is equals to mass times acceleration. So when we were solving the problem on the equilibrium, or when we were solving the statics problem, we says that my summation of force will be equal to 0, and then you can expand this summation to write like f1 plus f2 plus f3 equals to 0. When you have given f1 and f2, you can actually find f3 as minus f1 minus f2. So this was the major concept in the problem of equilibrium in the statics. But now we will say that my summation of force is mass time acceleration. So it is not an equilibrium. So my summation of forces equates to mass time acceleration. So if you have given f1 and f2, then you can find f3 by using this relation. So this we will look in the next class also. So that's it for today.